If we have a circle with centre C, and if P is a point anywhere on the circle, we can join C and P with a straight line, which is therefore going to be a radius of the circle. Now consider the tangent to the circle at the point P, that is, the straight line which just touches the circle at point P and nowhere else. An important result is that whenever we do this, the radius from C to P and the tangent to the circle at P will always be at right angles to each other. Now, it is not essential for you to know how to prove this result, and indeed we're not going to prove it now. However, it is the kind of result that when you look at it, you think, well, how can this possibly be any other way? There is so much symmetry in a circle. In particular, if we extended the line from C to P, it would become a line of symmetry of the entire circle. It's very difficult to see how this result could be anything other than what it is. So we have this result. The tangent to a circle is perpendicular to the radius of the circle. Here is another useful result. If we have a circle with centre C, and if the points A and B are any points on the circle, then we call the line segment which joins A and B a chord of the circle. So a chord of a circle is simply a straight line from one point on a circle to another point on a circle. If we now consider the perpendicular bisector of that chord, that is, the straight line which is perpendicular to the chord and which goes through its centre, then an important result is that that perpendicular bisector will always pass through the centre of the circle. Just for clarity, the point on the chord AB, which the perpendicular bisector passes through, is the midpoint of that chord. Let's call it M. So we have another result. The perpendicular bisector of a chord of a circle passes through the centre of the circle. Again, there is no need to prove this fact at the moment, but once again, with all of the symmetry here, in particular the line of symmetry of the circle, which is the line that passes through M and C, it is again really impossible to see how this could be any other way. So let's consider some questions that we can solve using some of these ideas. A circle has equation x subtract 4 squared plus y plus 3 squared is 5 squared. The point P has coordinates 7, 1. Show that P lies on the circle and find the equation of the tangent to the circle at P. Firstly, proving that the point P lies on the circle. One way this is very often done is by substituting the coordinates of the point P for x and y. 7 subtract 4 squared plus 1 plus 3 squared is 5 squared, and then showing that we get what we would expect, 7 subtract 4 being 3 and 3 squared is 9, 1 plus 3 is 4 and 4 squared is 16, 5 squared is 25, and indeed 9 plus 16 is 25. Now, I am here to tell you that you should not do it this way. Because if you are doing it this way, you are assuming that the result is true in your very first line. And you cannot prove something is true by assuming that it is true. So what should we do instead? Well, something remarkably similar, but not quite the same as this. We should begin by saying, if x is 7 and y is 1, then that means that x subtract 4 squared plus y plus 3 squared is 7 subtract 4 squared plus 1 plus 3 squared, which is 3 squared plus 4 squared, which is 9 plus 16, which is 25, which is 5 squared. Now we can conclude that P lies on the circle, because we didn't assume that we were going to get 5 squared until we actually got there. So let's illustrate this situation. Here is our circle. We know from our understanding of the equation of the circle that it has centre with coordinates 4, negative 3. We have just proved that our point P with coordinates 7, 1 does lie on this circle. Let's join those points with a radius of the circle, and we need to find the equation of the tangent to the circle at the point P. Now, using the idea that the tangent is perpendicular to the radius, we can get a gradient for the tangent by working out the gradient of the radius. So if this radius joins the points C with coordinates 4, -3, and P with coordinates 7, 1, then the gradient of the radius is the difference in the y-coordinates, -3 subtract 1, divided by the difference in the x-coordinates, 4 subtract 7. So we have -4 divided by -3. We have a gradient of 4/3. That tells us that the gradient of the tangent, being -1 over the gradient of the radius, is -3/4. Now we have a gradient of the tangent, and we know that it passes through the point 7, 1, so its equation will be, using the y minus y1, is m x minus x1. The equation of the line that we want is y subtract 1 is -3/4 into x subtract 7. The question doesn't tell us what form to leave our answer in, but let's tidy it up a little bit. If we multiply both sides by 4, we'll have 4y subtract 4, and if we expand the bracket that we're left with, we'll have -3x plus 21. Let's move everything onto one side. 3x plus 4y subtract 25 is 0. There's the equation of the tangent in a nice form. In this question, we're working backwards. It tells us that the points A and B with coordinates -4, 12 and 4, 8 respectively lie on a circle. It also tells us the equation of the tangents to the circle at the points A and B. And we are then asked to find the equation of the circle. Let's illustrate the information we're given. The point A with coordinates -4, 12 lies on the circle. The point B with coordinates 4, 8 lies on the circle. The tangent to the circle at A has equation y equals 12. The tangent to the circle at B has equation 4x plus 3y subtract 40 is 0. One thing that is always very important with questions like this is to draw a diagram. It doesn't matter if it's super accurate, it doesn't matter if you have the axes on your diagram, which is one of the reasons why they're not shown here, but it gives you a very good idea as to what is going on. Right, how are we going to find out about this circle? Let's begin by seeing what we can discover about its centre. We know that the perpendicular to the tangent at A is going to pass through the centre. We also know that the perpendicular to the tangent at B will pass through the centre. So if we can get equations of those tangents, then we can work out where they intersect, and we will know where the centre is. We don't have to do any hard work to find the equation of the perpendicular to the tangent through A. If the tangent through A is a horizontal line, then the line perpendicular to that is a vertical line, and therefore has the equation x is some constant. And that line passes through A, which has an x-coordinate of -4, and so we can see straight away that the equation of the radius through C and A is x equals -4. We now have to work on the perpendicular to the tangent at B. So the tangent at B is 4x plus 3y subtract 40 is 0. If we rearrange that into the form 3y is -4x plus 40, and if we then divide by 3, we'll have that y is -4/3x plus 40/3. In other words, the gradient of that tangent is -4/3. That means that the gradient of the radius through B is 3/4. We know that that line passes through the point B, which is 4, 8. So using y minus y1 is m x minus x1, we have that the equation of that radial line through C and B is y subtract 8 is equal to 3 over 4 x subtract 4. Now, why did we want this equation? We wanted to know where it intersected with the other radial line, which we know has the equation x is negative 4. So if we substitute x equals negative 4 into this equation, we will get y subtract 8 is 3/4 of negative 4 subtract 4. In other words, y subtract 8 is 3/4 of negative 8. Well, negative 8 divided by 4 is negative 2, times 3 is negative 6. That means that y subtract 8 is negative 6, which means that y is 2. Therefore, we have the centre of the circle. The centre of the circle is negative 4, 2. What else will we need to know about this circle to find its equation? Well, we'll need to know its centre, which we do know. The other thing we'll need to know is its radius. How far is it between the centre and a point on the edge? Well, we don't even need to do anything complicated here either, because the point A is directly above C. They both have x-coordinate negative 4. What's the difference between their y-coordinates? How far is it from a y-coordinate of 2 to a y-coordinate of 12? That's a distance of 10. So the radius of this circle is 10. So using the fact that we have a radius of 10 and we have a centre of negative 4, 2, we can therefore say that the equation of the circle is x subtract negative 4, x plus 4 squared, plus y subtract 2 squared is 10 squared. In this question, we're told that the point A with coordinates 2, negative 6 lies on the circle with equation x subtract 7 squared plus y subtract 6 squared is 169. The point B has coordinates negative 5, 11. Once again, we're asked to show that B lies on the circle. So let's remember the way we had to do this before. Substituting an x-coordinate of negative 5 and a y-coordinate of 11 into the equation of the circle, we will get that x subtract 7 squared plus y subtract 6 squared is negative 5 subtract 7 squared plus 11 subtract 6 squared, which is negative 12 squared plus 5 squared, which is 144, plus 25, which is 169. So B lies on the circle. Let's illustrate what we've got so far. We have a circle with an equation we're given. The point A with coordinates to negative 6 we're told is on that, and we have just proved that the point B with coordinates negative 5, 11 is also on the circle. Let's let the centre of the circle be the point C, and because we understand how to use the equation of this circle, we know that the coordinates of C are 7, 6. The next part of the question asks us to find the equation of the perpendicular bisector of AB. So we will need to consider the chord which connects A and B, and we now need to find the equation of the perpendicular bisector of that line, which we know will go through the centre of the circle. There are several ways we can do this. For example, we could find the gradient of the chord joining A and B and use the fact that the line we're trying to find the equation of is perpendicular to that. An alternative is to find the coordinates of the midpoint of A and B, this point M, which our line also passes through. Let's do that. So if we have the point A with coordinates 2, negative 6, and the point B with coordinates negative 5, 11, then the point M, being the midpoint, will have an x-coordinate which is the average of 2 and negative 5, and a y-coordinate which is the average of negative 6 and 11. Therefore the coordinates of m are negative 3 over 2, 5 over 2. Now that we know the coordinates of C and M, we can find the gradient of the line which passes through them both. So the gradient that we want will be the difference in the y coordinates, which will be 6 subtract 5 over 2, divided by the difference in the x coordinates, which will be 7 subtract negative 3 over 2. So we have 7 over 2 divided by 17 over 2, better written as 7 over 2 multiplied by 2 over 17, we have 7 over 17. Now we have a gradient, and we know a point that this goes through, the centre. We've already established that the centre has coordinates 7, 6, so the line that we want has equation y subtract 6 is 7 over 17 into x subtract 7. I'm not going to tidy this up on this occasion. We haven't been told for a final form to use. Just make sure that if you are asked for a particular form, you leave your straight line in the requested form. In the final part of the question, we're asked to find the area of the triangle ABC, where C is the centre of the circle. Let's draw some line segments joining the points A and B to the centre. So we can see that the area we're being asked to find is this shaded area. How can we find the area of that triangle? Well, actually, I think it will be slightly easier to find the area of half of that shape and then double it. So let's try and find this area. This is the area of a right-angled triangle with a right angle at M. If we knew the length from B to M and from M to C, we can work out that area by doing a half times the length BM times the length MC. But it's easy for us to work out all of those lengths because we know all of the coordinates involved. So reminding ourselves that M has coordinates negative 3 over 2, 5 over 2, and that C has coordinates 7, 6, let's work out some of those lengths. The length from B to M is the difference between the x-coordinates of B and M, negative 5 subtract negative 3 over 2 squared, plus the difference in the y-coordinates between B and M, 11 subtract 5 over 2 squared, and all of that square rooted. That comes to 13 root 2 over 2. We have access to calculators throughout the whole of this course, so there's no need to stop and do all that in lots of small pieces. And the length from M to C is the difference between the x-coordinates of M and C, 7 subtract negative 3 over 2 squared, plus the difference in the y-coordinates, 6 subtract 5 over 2 squared, all of that square rooted, which also comes to 13 root 2 over 2. Don't read any deep significance into that, it's just a bit of a coincidence of the way the numbers were set up in this question. So, the area that we are after is going to be 2 times, because we're only working out 1/2 of the triangle that we're interested in, a half times 13 root 2 over 2 times 13 root 2 over 2, which comes to 169 over 2.